All right, so I completed my rotation. I'm sorry, I didn't complete my rotation. I kind of did. I completed my opposite reciprocal, and I made this perpendicular line right here. So this is 90 degrees. You know what? It did not say clockwise or counterclockwise. For the sake of this, let's assume clockwise. Okay, so now we also lucked out because, remember, you have to also make sure that A and B are the same distance away. Now, in this case, remember like what we did before when we did reflection? I said figure out, you know, like where you are actually intersecting at the axis of symmetry. For rotation, figure out where you're rotating about. And if you can't actually calculate this distance, if it's not that simple to count and say, oh, however far this is, go, you know, use right triangles. You know, go down and go over some. Probably shouldn't have used green, but we went down 2 here and we went over 5 this way. And apparently that's the same as our slope. Now rotation's a little difficult because you have to figure out, you know, this is how far I rotated, whatever. And for the sake of problems like these, we'll always make these easy, like 90 and 180. We won't say something like 70 degrees and have you figure out exactly where we went over. But we do land on this point. We have to go down 5 over here and over 2. And it takes some practice, but one other thing that I did mention, and this isn't on a piece of paper, but if I took this drawing here and I was on a piece of paper, I would just want to rotate my piece of paper 90 degrees clockwise and say, okay, well, that's where my image ends up. So B, which I could also call A prime, but B ends up landing right here at the point 2, -5. I'm trying to see if that's the actual answer we needed. I don't know if we need the answer, but we needed to graph B. So B is at this point 2, -5. So let me erase all the extra work. Could probably erase the line as well. But I have A and B. Okay. Check that off. So now let's graph C, the image of A for a 180 degree rotation about O. So starting at A, we have to rotate this 180 degrees. So actually, I will mark this up again. If this is 90 degrees, another 90 would obviously be 180. But that means I basically take this line here and I straighten it out a little bit more. I just extend it out more. And it needs to keep the same slope, 5 over 2. And because this is point A, C is the same distance away on the other side. So C is right here. Can I click off? There we go. So C is right here at this point, which is -5, -2. Remember, we rotated 180 degrees. Whether it's clockwise or counterclockwise, in this case, it doesn't really matter. So this is 180 degrees. We have to find out how far away C is. Because remember when we do rotations like in this past one we just did, everything is the same distance away like it's on a circle. So I could, you know, bring out a big circle, you know, just like this and just say, oh, look, everything is, you know, that far away. Obviously, I didn't do that right about the center. But everything is going to be on this circle that far away. So if you can imagine when we'll do D, we do 270 degree rotation, I think we'll already start to see the pattern that D's right here. But if you can't, let's just do that right now. So D is a 270 degree rotation, and you might not know what 270 degrees is as far as you might have to do some adding. Say 90 plus another 90 is 180, plus another 90 is 270. Or it's 90 less than 360. So you could go 90 degrees counterclockwise and also figure it out. So D is that one that also should be 180 degrees about point B. All of these kind of have a relationship here. And it kind of works out for you that way. So let me actually just take this and take it out just like I did with the other one. Like that, it should cross through the origin, be at the same slope, and D is the same distance away from the origin just like all of the others are. So here's point D at -2, 5. The final thing they ask you is what type of quadrilateral is ABCD? Now this isn't a quadrilateral, but you have to now draw a quadrilateral about these. So let's do a thick one like that from A to B, from B to C, from C to D, from D to A. So what kind of quadrilateral is this, and explain? Well, there are some things that we know here, and we can use these measurements to actually talk about that. Keep in mind that the distance from O, let's call it O, the distance from O to C is the same as the distance away from O to B. So that means that these are congruent lengths. And this is 90 degrees right here. So you are looking at an isosceles right triangle. And an isosceles right triangle means that these angles are congruent. Not only are they congruent, but we can say they're 45 degrees because that should all add up to 180. And this is 45, and the same thing applies to all of these as well. So this is 45 as well, like so, and 45s. So once you start seeing that pattern, you're going to say, oh, look, that means this is 90 degrees as well. And so is that, and so is that, and so is that. So you end up getting, at the very least, you end up getting a rectangle. You know that all of these are right angles. The other question is, are these congruent? And you can do whatever double checking. You can do some recognizable patterns and such. Maybe you can find some way in trig. And in fact, yeah, you could find trig in figuring it out. But the important thing is figuring out that distance anyway. So you can use distance formula and go from here to here, and distance formula go from here to here. Or maybe if you just picked up enough cues, you can say they are congruent. AB is congruent to BC, etc. So the name of the quadrilateral with all four sides being congruent and parallel, for that matter, opposite sides being parallel, and all the angles being right angles is called a square. And also, obviously, that'll be the next couple problems. And also, obviously, if it's drawn correctly, then you can rotate your head and maybe even pig out that it does look like a square. But mathematically speaking, we can also determine that as well. And explain congruent sides, right angles. Okay, number 6. Find the image of each letter. In this case, it's just this one particular problem. Find the image of the letter T. Let's just say T. Through a reflection in line L, and then a reflection in line M. So let's reflect across here first, and then from there, let's reflect across there. Describe the resulting translation or rotation. Now, they don't give you any actual units, so you won't give any units out in saying what it is, but you can still give a description based on the notes that we've taken. Okay, I guess you don't want to erase. So you can rough these out a little bit. You don't have to be perfect, but you do want to give an example of what this T should look like. For instance, now I'm going to clone it because I can. Oh, you know what? I think I've done group this first. Right. I'm going to clone this because I can, and that way you can actually get a better example of what we're looking at. And I'll give it a different color as soon as I find it. I like to use orange for the translation before the actual image. And if we reflect across line L, keep in mind that looking into a mirror, if I had a perpendicular, if I had a horizontal axis of symmetry, okay, then it would be straight up and down like this. But I'm looking into a mirror that's a little bit slanted. And so if there was a multiple choice question that said, what is the reflection of T? And I'd say, is it that? Hopefully your answer is no, because you do have to keep in mind what every point should have as a reference. In other words, going from here straight down to the mirror, or perpendicularly to my mirror, and going from my mirror to that should be the same distance away. So should that from that and that from that. And if you've seen these reflections enough, you know it's more like this, where these distances away are congruent, like that. So it doesn't have to be perfect, but there's an okay example. Now we have to take this T and reflect it all the way across M. So for me, this will end up being less perfect than the other one. But there is something that we learned. And that is, when we reflect across two parallel lines, that is the equivalent to a translation across the lines where our distance covered from our pre-image to our image is twice the length of that between our two lines here. So let me kind of restate what I just stated. And this might not be perfect. I'll try and figure out where I want to go from here. But if I take a point on T, like a vertex. If I take a point on T, let's reflect it across line M. So we have to find that opposite reciprocal. We have to find that perpendicular line. Oops, I have to use these. So let's just draw something that's kind of roughly going through